Okay, may I have your attention, please? Good afternoon, and thank you for being here on this special Carnival edition of the Jones Seminar. I would like to introduce Scott Mitchell, who is our speaker today. He graduated from Hobart and William Smith College with a BA in economics. He's worked at several high-tech companies since, including Raytheon, Dialogue Systems, Ortho Diagnostic Systems, Martin Marietta, and American Science and Engineering. Scott now works for Creaform, a Canadian company based in Quebec that makes handheld 3D digitizers. We use one such scanner to acquire anatomic information on patients. The folks in the machine shop, and Kevin here has one, use it for any number of applications for projects. I invited Scott to give us an overview of the range of applications for this kind of 3D scanners and how it is changing the design process. Please welcome Scott.
Now, can I be heard? Yes. Good. Thank you for inviting me here. It's a pleasure to, I think business and academics, it's they're kind of two different worlds, and some people veer towards one and towards the other. But I think there's a huge amount to be gained by maintaining a dialogue between both, the commercial world of business that I'm in and academics. I should say, my bio is mainly coming from the School of Hard Knocks. I just spent years out, in commercial business, last 20 years in technical sales. So what I like about it and what I hope you'll see during this presentation is, especially in the 3D world, there are just so many interesting and innovative things going on, and it's fascinating to me how people, for example, I just took a tour of your lab here today. They're using the view scan to scan the surface of breast for different types for creation of new diagnostic tools. I'm always thrilled when I see stuff like that. People using it, taking the technology, and then moving a step forward. So what I first want to talk about is about measuring, although, I don't know, what's my mix here? I mean, are we all engineering? I'm just trying to get a feel for, because this world, like the video I just showed you, is actually, it lives in the artistic side of the world. I don't know if you could see briefly that was a tree and a young lady that was, was all digitally compiled, but from real scan data. So a lot of the engineers at Creaform actually, like most of us, we're not just engineers and we're not just artists. Most of us have inclinations in both worlds. So I guess I'm curious if, am I talking exclusively to engineering here, or am I seeing a mix of art students and so forth?
Yes, mostly engineers.
Mostly engineers, okay. But I'm going to guess that there's some engineers here that also have artistic proclivities. And the reason I say that, so you laugh, so yes, no, maybe? Okay. The reason I bring that up is in the 3D world, we're not just looking at traditional geometries. We all drive cars, so we all know that the cars have a lot of features in them that are prismatic shape, meaning the geometric shapes, bores, holes, cylinders, stuff like that. However, if you look at the new products in the world right now, there are more and more there's an increasing use of what we call organic or free-form shapes. And the problem becomes, how do you, if you're going to manufacture product, how do you analyze your controls? how consistent is your product if it's a very, very extreme free-form shape. I mean, I'm grabbing this bottle, which we could say is, it's got a mixture of, there are some cylinder-type shapes here, but there's also a lot of tapered locations. As you know, somebody designed a tool, a blow mold tool for this. So how do you control this? How do you inspect it? I also worked for Starrett years ago. This is, digital caliper, traditional tool. So if I want to measure something, right, I can do this. But how do I measure this thing when I've got organic shapes? And the answer is 3D scanning. So let me put this down. And what I'm going to do is just give you a very quick scan of an object, because I think the goal of this meeting is, what I would like to communicate with you is, first, I'm not here to do a product sales pitch, even though normally that's what I do. That's my job. I'm in sales. But what I want to do is have, when you come out of this, if you're thinking about, wow, 3D, this could be interesting for something I'm working on. That's the goal, is that if I can, stimulate some additional thoughts in your minds about either projects you're working on now or that you might be working on in the future. And these can be, I can't tell you the range. I talked to a guy on the phone yesterday who's retrofitting bridges, ailing bridges in the DC corridor, 495. Rotting, rusting bridges, and he's got to reverse engineer and then rebuild the structures. And he wants to bring a scanner up on a man lift and try to acquire data off the bridge because there's no drawings. He's got nothing. So how's he going to put in new parts if he doesn't know what the features are? So there's just so many different things. That's my goal of this meeting, is to have you guys think about, maybe I could use it for this, or maybe I could use it for that. I'm just going to do a very quick scan, and before I do it, I work for Creaform. It's a company based in the Quebec area up in Canada. And Creaform, just so you know about it, got started about 8-9 years ago. Their line of work was, and still is, doing custom inspection projects for aerospace, Pratt & Whitney, Rolls-Royce, people like that. And they found that the tools for measuring at the time were limited, so they decided to start creating their own tools. And the result of that design, one of them is called the Handy Scan. This is the ExaScan. Professor Hartov has a ViewScan, which is a 3D color laser scanner, and the machining group has a ExaScan just like this. So you can take any object of any type and you can put these dots on it. They're small adhesive dots that they're either magnetic or adhesive. And we have drapes, we have other types of arrangements, but basically you put dots on it. And then the scanner, it helps if I turn the scan button on, works a lot better. It's basically digital spray painting. So all I'm doing is going around this. It's just a phenolic hubcap. I carry it because it fits in my briefcase, because I travel all over the place. So this is my handy target that I use just to go around and scan. And what you can see is I can just go around and acquire data off of this. And instead of spray painting paint, what I'm doing is I'm creating a digital model. You notice as I tilt, the model tilts. As I rotate, the model rotates. So what's going on here is it's using these dots to track the position of the scanner with respect to the object. Because what we're trying to do is make a geometrically accurate model so that we can take the model, we can process the model, and you can see in just a few short moments we're looking at a 3D rendition. At trade shows, one of the fun things people do is they'll come up and I'll put dots in their face and we'll scan faces. So if any one of you want to have your face scanned, just come on up. We'll get it over with if we need to. But it's in fact, here's a lot of people after they leave my booth, they have dots on them. I'll pull out some dots momentarily, and they wear them like a badge of honor. Here they are. So I'll put one on my forehead because often when I'm at trade shows, I end up with dots on my forehead. And as long as they keep their face still, here's the hard part. If I'm scanning your face, the hard part is the dots have to stay fixed because they're kind of a reference to build this digital model. And if you smile, you can move your head, but you can't smile and make the dots move. So, okay, what's the point of all this? Fair question. Is we end up with this is essentially the digital file that's created from the scan, whether it's your face, the hubcap, whatever it is you're scanning. And then the question is, well, what can I do with that? And the answer is, well, I can go and I can measure things with that. I can construct best fit features off of it if I want. So I've just constructed granted it's a pretty, it's some pretty lousy data there, but who's going to be fussy, right? I can select data anywhere I want. So the reason I'm showing you this is to plant the idea in your mind that with a relatively fast scan of an object, you can analyze its geometry and measure it. So, any thoughts as to what that might be useful for? No takers. Okay. Cloning? Absolutely. Reverse engineering. Reverse engineering has kind of a dirty name for some people. It's but in fact, there's a ton of reverse engineering. I met a gentleman who had a major accident on his face, and he lost. He had major skull fracture and lost an eye, and so I scanned the good side of his face and the bad side, so that they could design a prosthesis that would not only fit his existing face, but we can flip the image over and then create a normal prosthesis. So reverse engineering, here's another good one. I was at Adidas. We call it Adidas, and I think Shaquille O'Neal has his, the big stars have their shoes made and they use the PR Nike does. They all do it. It's big money. Well, anyway, so I saw his shoe, and it's like a size 22 or something. It's outrageously large. I think I could live in this shoe. But they can scan his feet and then design a shoe right around it. So just in consideration of that, cloning, think about it. Most manufacturing today is, potato chip, right? It's like we're going to make whatever it is, and we're going to make gazillions of them. How about in the near future where we're not going to do that? What we're going to do is We're going to make it, it's going to be like Burger King, have it your way. We're going to scan your body, and then we will make a shirt or a jacket. It will be made to fit you. You know, because everybody is shaped differently. And just think of the implications. That's the whole world of rapid prototyping. That's what they call it now, and it's done mostly on a prototyping basis. But if you think about the fact that modern manufacturing will be done customized for each one of us, you know, think of the possibilities of that. Okay, on the engineering side of things, of course, the other part is if you've already designed something, you want to be able to compare. I assume some of you folks are using CAD here. I heard there was SolidWorks here. Is that okay? Any other CAD platforms here? Pro-E, yeah, okay. So, have you been asked to do some design in Pro-E? What did you make?
Used to design the bridges for 33 in Pro-E.
Bridges as in the kind we drive over?
Well, a small scale.
Oh, okay, gotcha. 2 feet, okay. Oh, for structural. Oh, well, that kind of gets to FEA. We touched on FEA. You can scan, you see these triangles. And I'm not familiar because I'm not a mechanical engineer, but you can take this data, scan an object, and then dump that model into FEA software, and then I presume you use it as a basis to perform a variety of calculations based on the material strengths, yada, 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 whatever. Another thing you can do, though, is you design something, then you fabricate it. I have to say that, as I mentioned earlier, I come from the School of Hard Knocks, so my observation of mechanical engineers, for example, coming out of school is they usually are pretty good with the theoretical, the design stuff, the FEA. But a lot of them, of course, when you're right out of school, you haven't really bumped into manufacturing. So I'm just going to put this out because this is my few times I can speak to future engineers while they're still in school. So my little platform here. Sorry, but there isn't a lot of attention paid to tolerancing. I don't know how many people are being taught geometric tolerancing, but it's one thing to design the thing that you want. It's another thing. To me, that's only half the information. The other half of the information is how do you tolerance it so it's producible and it's competitive. And that's a huge piece of the design world, because if your tolerances are completely out of whack, then you've designed a wonderful thing that's not producible. So I hope that, and I have to say, geometric tolerancing is sort of maybe it's a bastard child in the engineering world. I don't really know, but that's the language that communicates to the fabricator. What can I get away with? How can I keep my costs down and still fabricate this part on a competitive basis? So anyway, okay, that was my little lecture. So if you designed it already, now you're going to fabricate it. We all know there's variation in fabrication, right? There always is. Variation is a fact of life. So clearly people have to analyze okay, you've done a good job, you've designed something. Now, what was made, and how does what was made compare to what was designed? So how do they do that now? Right, we get, in the world I grew up in, it was a 2D print and tools like this. So if you design this cup, I'd be sitting here measuring the ID with the ID gain, the OD, and blah, 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 blah. But things are no longer like this anymore. Things are getting complicated. So one of the huge tools, maybe I'll just get to the point, stop dilly-dallying around. One of the great tools is now with 3D tools like this, we can analyze quickly. We can compare the CAD model, pull in the scan model, we can align them together and find out how they deviate. So I'll do that for you here in a moment. We can also scan an object today and scan it in 6 months, or we can thermally change it. We can perform some kind of a test on it, a load factor test, and then scan it later and see how the geometry has changed. Yes?
So how does the variation of the scanner hold up versus, like I can understand that there's some variation will definitely of the scanner. And how much you contribute to it if you want to do a quality check of your product.
Okay, so no, what's the accuracy of the scanner? Okay, on small volume, of course, this is just one type of scanner. There is a whole family of different types of scanners out there. Where we merge photogrammetry, structured white light. There's a lot of different ones. But let's just talk about this one right now since we don't have a huge amount of time. So what I'm going to say is, and I wrote this down earlier, that the error equation for this, I don't know if you guys think in inches or metric. This is 20 microns. Is your baseline error. So that means that thing it's no more accurate than 20 microns. And I will tell you that in the world of 3D, if you have to measure a bearing race of a racing engine, a bearing surface to plus or minus, it's not unusual for bearing surfaces to have tolerances like this. What we call 5/10 or half a thousandths, whatever you want to call it. You're not going to do that with 3D. Not with 3D scanning. You'll do that with, when I turn my head down, it gets really loud, doesn't it? Oh, okay. You'll do that with either air gauges or bore mics, or you'll use a Zeiss CMM or a Mitutoyo CMM. So, in the world of 3D scanning, this is not the most accurate, but where you are in the world of 3D scanning is in this order of magnitude, plus or minus a thousandth of an inch. So any kind of measurements, and the gauge rule factor for inspection says that if my measuring tool can only measure to this accuracy, then my drawing tolerance should be no more than a factor of 10, or no less than a factor of 10. So if I have a tolerance of plus or minus 10 thousandths on a feature, I can still use this tool. But if I have a tolerance of 5 thousandths, it's a 10% rule. I don't know if you've run into it or not before. So yeah, that's a good question, because clearly there's some stuff you're not going to measure with 3D scanning. And it also lives in the macro world, too. It's not micro. We're not looking at angstroms and 2, 3, 4 microns, that kind of stuff. Not there. Yes, sir. Okay. On a turbine blade, the airfoil section of the blade, and usually there's a deck here, and then there's what we call a root structure. This section is often plus or minus, 10 thou, or 15 on the airfoil itself. But the root is where it ties into the main engine rotor. That's tight. You're talking much tighter tolerances. You're not really going to use 3D scanning for the root structure of a turbine blade. Not going to do it. Every tool has its place. No one tool does everything. So that's just the way that is. I'm going to just, I'm really not good at following a script. I'm just going to kind of jump around at some different projects that I've worked on recently. I'm going to kind of move over to the artistic side of things right now, and then we can talk about, and I want to do measurement too. So there's, but I'm going to dance around a little bit here from one side to the other. I was at the Metropolitan Museum of Art in New York, and it was really pretty cool in the Met. They have a bunch of scientists I was working with, physicists and conservators. There's a bunch of degrees. I don't know, does Dartmouth have degrees in conservation? It's kind of a specialty, I think. Most of the people seem like they were from Europe. But what they do is they restore ancient items, statues, paintings, and oddly enough, it's funny, they bunch themselves in the world of 2D paintings and stuff. That's one specialty of conservation. And then there's another side of it, which is statues and anything that's 3D, whether it's an old piece of carved furniture from the, Middle Ages or whatever. And at the Met, they have these rooms. There's like 4 city blocks underground of all this stuff that's covered, it's draped in, sheets. And a lot of it's damaged. And what they're looking at doing is, can we fix it? But if we fix it, gosh, are we going to get out the Elmer's glue and slap it together? And I don't think so. They use scientists and technical people to say, okay, what's the best approach? Because when you go to fix this statue, it was made in whatever year, it's a one-shot deal. You're not going to, you know what I mean? Not like the way I'd fix something at home. So let's go look at something that we did. Metropolitan. Now, a lot of stuff, when we go do projects, I can't show, I sign disclosure agreements. So what I'm going to show you is a kind of a coupon, a test, which is done, of course, with load factors in engineering. We use coupons all the time. So this is essentially what we did. They said to me, Scott, take these 2 pieces of marble that had been broken, and because probably, I'm guessing, one of the statues had a broken arm or whatever. Some of these statues are broken in 15 places, and they're trying to restore them. So what I did was I put these little targets, like the one that's probably still on my forehead, and I just put them on the marble, and then I scan it right here at the table. And then what I do is I separate it. And then I scan that surface. Because, okay, I didn't tell you why. That'd be helpful if I explained to you why. What they're trying to figure out is, if you're going to bond marble of an ancient statue, you want to know what the interface surfaces are like, because evidently there's many different types of bonding compounds with different solids levels and whatnot. So they need a digital map of, are there only 3 contact points? When that thing's broken, because they probably get a statue in a box in 10 pieces. They want to know how much real contact exists in the fracture area. Am I making sense? Okay. So here I'm going to show you a report of the scan result of that. So we scanned it, and what we do is we define a certain bandwidth of material as we just arbitrarily define as plus or minus 20 thousandths. Are we in microns? I can't see the scale here. Let's see if we see the scale. So we have one part here. And then what we really are interested in is the interface between the 2 of them. What this is, you can select any point you want, and it's the difference, it's this gap between the surface of the broken part and its mating part when it's fixed. So in other words, the reason I showed you a picture of them put together is I put them together. The software sees it in its assembled state. But then by opening it up and scanning the interface, the fracture area, it allows me to, it'll reassemble it digitally. We call it digital assembly. And then we can analyze the gap and mating surfaces between the pieces of marble. And we can make nice little reports. We call these Whisker Plots, and we can scale factor these. So they're colored by the bandwidth, yada yada, how you set your tolerance. This allows the conservation engineers to know where their points of contact are and how much gap they have everywhere throughout the fracture area. So they know what they have to do in terms of whatever bonding process they choose to use, which they're not going to tell me about. It's none of my business. That's their deal. Any comments, questions about that?
Why are they so secretive? Seems like this is something that lots of museums across the world would be interested in. Open source, let's fix it together.
I'm sure that the conservation technical staff, I would guess that they do share. Actually, this was done jointly with the Met and the Smithsonian. They just don't tell us about it because, well, I don't know why. Of course, we sign non-disclosures, so at the end of the day, the way I look at it is if they don't tell me, it's because they don't want me to know. And I do scanning, let's see, last week I was at Pratt & Whitney. I'm going to show you a few other things. There's, obviously, when you get to military, there's a lot of security, yada, yada, yada. So if they don't tell me the way I figure it is, okay. I guess I don't have a need to know, even though I'm curious. Certainly I'm curious. Who wouldn't be? In fact, somebody mentioned an airfoil blade. This is actually a standard procedure we use for airfoil scans. I'm just kind of blasting through it, but it's actually a procedure we wrote up. We do so many of these kinds of airfoil components that it became, beneficial for us to just write a procedure for scanning airfoil components. Okay, I'm going to move to another completely opposite. Like I said, I'm dancing all over the place. That was sort of the art preservation side. I think I'll move to nuclear submarines now and just talk about them for a moment. Where did I put that? I think that's over here. Or maybe it's here. Oh, okay. Now I didn't do this. Okay, this is something else. This is on the medical side. Rhinoplasty, as in nose, I take it. Now, I did not do this. I was not part of this. But this falls into the same bucket as the scan I did on the guy's face, where we cut a symmetry plane and then we flip the data over and then we can design a... By the way, of course, we all know that actually our faces are not particularly symmetrical. In fact, I guess our bodies aren't very symmetrical either. But if you're going to design a prosthesis, that's probably a good way to go. Right? I met some guys at Penn State. At Penn State, they do a bunch of consulting work for the U.S. Navy. That's where they design the torpedoes. And now what they're doing is they're working on this is a mock-up we did. We made a mock of you can see it in the upper left, a mock-up of a submarine. Well, I touched briefly on rapid prototyping. Here's the scenario with a sub. A Virginia-class nuclear sub comes into a dry dock. They drain the water. Every day in dry dock is something like, I don't know, $300,000. I mean, it's big bucks, a dry dock at a Navy shipyard. So right now, and the subs are covered in a 2-inch thick rubber tile. Because we all know submarines, stealth is the name of the game. So they use absorptive materials that are classified to prevent them from being sonar detectable and probably some other, they're special rubber materials. But at the end of the day, they kind of look like 2-inch thick rubber tiles, and they're in different shapes, whether it's Seawolf or Virginia class. They've got different tile shapes. They come in, and guess what? The tiles are smashed up. I don't know what those subs are doing down there, but they must be banging into things. So they come in with damage, and those tiles have to be fixed. Now here's the challenge. The steel hull of the sub is got piping on it, so it isn't just a nice smooth. In some cases, it's got electrical conduit. So how do you fix the tiles? You get up on a man lift. These subs are huge. You get up on a man lift. You're bouncing around. You take out a tape rule and start measuring where the broken tile is. That's more or less what they're doing. What we just started was using our Max scanner. It's the big brother of this. It's combined photogrammetry and surface scanning. So you go up on the man lift and you scan the damaged area. Then you take the data, you surface it in a Geomagic or a Polyworks, and then you send a cut program and you actually have them cut out new tiles that exactly fit. Here's the tough part, though, is you've got curvature. Subs are not squares, we all know, and you've got actually different kinds of curvature in different places on the submarine. So it's actually a fairly complex program to scan it and then generate cut data for replacement tiles. But the fact that somebody's doing that, and this, by the way, is not fully operational yet. It's still in the development stages, but it's going to cut down the time in dry dock for repair of tiles down by something on the order of more than in half, like 70% reduction in time. So, since you're all wondering what's going on with your tax dollars, there's one little piece of it right there. Any comments and questions before I move on to some other bizarre and unusual scan projects? Okay, I'll proceed. One that I don't have any data for, I mentioned briefly, was I went to the Smithsonian. This one blew my socks off. There's these storage rooms at the Smithsonian. Guy comes to me, he's interested in the view scan like you have, Alex. And he said, I got things to scan over here. And I looked at them, and it was Langley's. Didn't Langley make one of the first planes just ahead of the Wright brothers? I think it came out 1890s or something like that. It never flew it because he didn't have the power. It was a steam engine rather than a gasoline that came along when the Wright brothers did their thing. I forgot when the Wright brothers, when did they, was that 1910 maybe? I don't know. Was it? Okay. Anyway, so these are Langley's parts. So they're still waiting to be scanned. But I thought, because he's trying to get budget, Smithsonian's on a tight budget now. But, I could just picture, if somebody could scan Langley's parts, they could actually maybe do a flight worthiness test in, they could model it. I don't know, that just seemed like a really cool, that an aeronautical student could look at Langley and say, if he only had 10% more horsepower or a little more wingspan, that would have flown. That would have been flight worthy in a simulator. It's amazing what stuff is out there. You mentioned something about sort of the design, the design cycle. What was it you were, when I first got here, Alex? Right. Yes. So, you kind of know what goes on in the design world, it's kind of a circulating loop. You know, somebody designs it in CAD, then it goes into prototype, then it goes into full fabrication, and then they say, oops, let's make these changes, and then we go back to the design. Because, I mean, we all know hey, what do they say about buying a first year model car? You know, don't do it because they haven't ironed out the bugs. One of the key elements of 3D scanning is to allow, using a tool like I just did here, it will allow us to, how is this? Wrong order, sorry. But we all know what submarines look like anyway, so I'm going to put that away. Yeah, anyhow. Here's, you know, as you know, the manufacturing world is very competitive. There is increased pressure to get products out quickly, get them designed, get them prototyped, get them manufactured. And today, you've seen it. If you look at Apple, any of the designers, whatever they're making, I don't care if it's electronics, cars, cycle time on development has got to be cut. It's got to be bada bing, bada boom. So, what are car makers doing now? Car makers will scan fenders now digitally and then go direct to tool design from the digital scan. And they'll do it on if they decide that the 132 model of the car is what they want, no problem. Let's scan it, and if we think it's good enough, we'll use that as a basis for our tool design. Now, you compare that to what happened 15, 20 years ago. I mean, I don't know if you're familiar. I mean, I'm not an expert on how they make body parts for cars, but it's a whole series of negative and positive casts and molds that's extremely lengthy. Tedious. It took forever to release a new car. Today, using 3D scanning, they're blasting. So there's more and more pressure on inspection and scanning groups to turn around stuff quickly. So let me show you one of the tools that I use and that's out there. I mean, a lot of people use this stuff. I'm going to go bring in some data. This is just going to be a quick example of how you can generate deviation models. Oh, here's another, speaking of a deviation model. As I mentioned earlier, you can compare a before and after. So what we did at NASA, I was out at the icing research tunnel at NASA. In fact, I'm going to just go there real quick. This is not classified, so we're just going to go take a look at this. NASA GRC. Okay, this. Oh, I have a pointer. I forgot about that. Oh. That is the profile of the airfoil, the leading edge of the wing. So they they put it in an icing tunnel, they drop the temperature to say minus 10 or 0 degrees, whatever their test plan calls for. They accelerate the wind to, 230 miles an hour. So what they asked us to do, though, was we scanned the airfoil itself with pretest scan. That way we know what the shape is. Then they run it through the cycle in the icing research tunnel. It builds up ice on it, and then we scan it again. Just like the knee, there was a young gentleman here who I met who was dealing with the knees. With ice, we have to put the powder on it because ice absorbs laser, so we sprayed it with a white powder. If you want, I'll tell you what, I learned something real quick about why planes go down with ice. I don't know if you can see up in this area, that is how, when we scanned it, that's how the leading edge looked with ice buildup. So if you can picture air trying to stream over that and gaining lift on a wing, I think you've got some big problems. What do you think? So this is a good example of, in 3D scanning, how we do before-after. There's a ton of uses for that. Anything you design in the future, if you want to see, condition A, condition B, expose it to load, expose it to, whatever your test parameters are. Scan it before, scan it after, line the models up, which I'll do for you now, and then you'll know exactly what went on within the limitations of, couple of thousandths of an inch. We're not talking, again, understanding the limits of the technology. So let's go to qualify. I'm going to load an IGES model. The example I'm going to use here is just to kind of give you a good view of what a NURBS model looks like in CAD. I mean, I'm sure you guys, engineering school, everybody uses CAD, or most, not everybody, but probably most, use CAD of one kind or another. Does that look like a CAD model to you? It looks nice, sterile, nice sharp edges, all clean, everything looks wonderful, yada, yada, yada. But it's not real, of course. So what I want to do is I want to bring in, oh, it can't, huh? Well, I'll see about that. Here's what I'll do. I'll dump it in here. Okay, we're going to drop this in the qualify. Bear with me, these scan files are obviously, they're bigger files, and I'm running a little 64-bit machine here, you can imagine how that's going to look. Okay, let's do this now. Bring this in. I'm going to load the scan model in. Now, you can tell this looks more like a scan model. Can you see the edges here? You can kind of see how we've lost. When you scan stuff, you don't always get everything. You miss stuff. That's the real world. And you can see there's sort of an as-cast surface here with a stamping on the side. So what I'm going to do is I'm going to do a comparison of the two. And I'm going to align them together. This is where we take, I'm comparing to CAD, but I could just as easily be comparing between two scan objects. Okay, now it's aligned it in space. And here's where the fun begins. May not look like fun, but it's kind of fun. Now what I've got is the two items, one overlaid on top of the other, and I've got color deviation models that tell me where I've got problems. I can just flip this around. If the CAD is, the color tells me, this color bar, says that I've got negative material in my machine part, which means I machined out too much in that case. If it's positive, it means my object is too large in that area. So what we're doing is comparing, think of the CAD and the actual scan model, and how are they negative, positive, or within my accepted bandwidth. And I can go in here and I can query this anywhere I want. 084, that's within whatever my nominal happens to be. That's in the negative side. So this may look run-of-the-mill, but I got to tell you, the ability to take an object and to analyze its deviation everywhere throughout the object is, compared to how we used to have to be able to do this stuff, it was impossible. You do point measurements, you do measurements with a digital caliper. There'd be no way to do this. So now we've got these great tools that allow us to analyze now if you've designed a mold or a tool or a CNC program to cut that part, you know where you've got issues and where you don't. And then there's some other nice tools. I'm going to try a different plane. I can cut this any which way I want, and I can translate it any which way I want. And now I can see where, based on a digital cut, where I deviate between the model and the CAD model and the scan model. So this is, in the engineering world, this is pretty good stuff, because a lot of molds are clamshell molds with cavities on the inside. We'll use digital assembly, then we can digitally cut through and see what's going on. Now, is this being used widespread across the industry? No. It's still just getting going. Still just getting going. But these techniques are going to make a huge difference and that's why I'm happy to be here today, because as you guys get out there and you start doing engineering work like this, you're going to start seeing, I want you to say, hey, I remember that technology. There can be a better way to do this. Comments, questions? Shoot.
Question on what does it base itself to align the actual part for the CAD model?
I just did a quick and dirty best fit. What you normally, if you're comparing a CAD model to a scan model, you'll normally use the CAD datums, which are usually predefined in SolidWorks, and then you'll use that as your alignment. And that's a good question, because a bad alignment gives you data that's junk. It just means nothing. Yeah. Yes?
The object is just scanned. Do you have information about the absolute mass of the part or the absolute radius? Say how much is the radius? Because when we measure something, we have to compare it with a point, so we know the absolute mass.
Well, the CAD model is the nominal, of course.
No, I would say just the object is just scanned, and then.
Oh, do I have the CAD?
No, I mean, from the scan, do you acquire the absolute measurements of the object? Is that because you know the size of the dot, and then you use that as a kind of a comparison?
Oh, yes. Okay, okay. Yeah, what you're asking is, how does the scanner work? Sort of. Yes, these are nominal 6 millimeter diameter retroreflective dots, and it does know the nominal size of those. The software, the minute it sees them, It identifies each dot's location in a text file in 3D space. And you're right, it's based on, well, there's a calibration grid that comes with the scanner. So it uses these 6 millimeter sizes to reference the overall shape and size. This is a ceramic calibration plate with 6 millimeter dots. So it turns out that the dot sizes of these adhesives is not all that critical. It's just to identify it as a positioning dot. Once I do this calibration, the software retains the calibration factors, and it gives me the spec accuracy. So I don't know if I probably gave you part of the answer, but not all of it, right? There's a ton of code. The fact is, with a scanner like this, the hardware might be, it might be worth $5 or $10 grand, but the rest of the money is all about code. And there's a ton of code. There's a lot of things I could talk about in the development of 3D scanning technology, the different types of 3D scanning and all that. But at the end of the day, what you're paying for with scanners like this is the code sufficient so you can just scan something, know that it's geometrically valid within the specifications of the tool. It just is. In fact, if I went to scan, I'll just give you, there's a whole series of check algorithms that are just a standard part of the tool. Oh, that's qualified. I don't want that. Let's say I pointed at myself. I'm going to resume scanning. It just doesn't acquire. If it sees no positioning dots, it knows that I can't. If I'm too far away, it doesn't acquire. If I'm too close, it doesn't acquire. So it's got a whole series of check algorithms to make sure that when I'm in specified range, okay, I can acquire now. That's kind of what you're paying for that, and you're paying for the fact that with others, there's some cool scanners that are a very low price point, much lower price point than this kind of scanner. But the way they stitch their models isn't precise within specified boundaries. So the reason people, if they pay money for this, it's because we need to know when we're scanning, we're getting a X level of performance every time. Yes? It's inherently limited. It has to do with the ability of the laser. Actually, these LED lights are only to illuminate the targets, whereas the laser crosshair, which, does it show up on the ceiling? Oh, maybe it doesn't. How about there? Nah, still not strong enough. You can almost see it. The crosshair acquires surface data. The LED lights acquire targets. And the answer is that there is a limitation in the optics and the sensor that I don't fully understand that essentially create a noise level and the noise looks like, as you would expect, if I scan a tabletop, if we saw the raw point cloud, you may have heard the term point cloud, there's going to be a distribution of points above and below the true surface. And what we're saying is they'll all fall within a band of about 20 microns. And you can't really, with this technology, you can't get much better. You can, with structured white light scanners, get a little bit better, but at the end of the day, 3D measurement tools are still essentially tools for, measurements in the thousands, but not below that. Yes, sir?
What are the upper limits to the size of the object? You mentioned this guy working on a bridge. Is he scanning the whole bridge? Or?
Yeah. Well, you could. One analogy I make for that is, there's two problems. One is, if I was going to if I was going to scan the door, you know, I'm going to start laying down dots, you know, and there's going to be a lot of dots, about every 3 to 4 inches. So one of the limitations is, you know, how many dots are you going to lay out? That's going to take a while. The other part is, think of this as a digital paintbrush with about a 10-inch field. So if I'm going to paint this whole auditorium, a 10-inch paintbrush, maybe not as good as a big spray, you know what I mean? It's just going to take you too long. And then, of course, you've got the stacking error equation I put up there earlier, that for every additional lineal feet of scan, you gain an error. So I don't know if I'm wandering off. I don't know if you folks have run into photogrammetry at all, but that's a technique where we use digital cameras and what we call coded targets that allow us to have, and scale bars that allow us to have higher accuracy over longer spans. So the answer is I could scan the Empire State Building, but I'd probably die of old age doing it. The error would stink. It would be tons of error, you know. But theoretically, I can scan. It's like you got a small paintbrush. You can paint anything you want. Yep.
I invite anyone who would like to find out more to talk to Scott. Thank you, Scott.
You're very welcome.